Hi, my name is Jonathan Fuller, and I'm going to give a short presentation about pseudo-ductility of thin-ply CFRP angle-ply laminates, work that I've done with Mesam Jolavand and Michael Wisnam. To introduce, this work has been part of the Hyperduct High Performance Ductile Composite Technology Programme grant, which is collaborative work with us and Imperial College. And the key aim of this work has been to create a paradigm shift by realizing a new generation of high-performance composites that overcome the key limitation of conventional composites, their inherent ductility. And my work, this project, has been looking at pseudo-ductility through fiber rotation and damage suppression in thin-ply angle-ply laminates. So why do this work? Well, many parts of the literature have shown that predominantly angle-plies fail due to matrix cracking and then free-edge delamination, which, as the graph shows, leads to a premature failure, which is the line in red. Now, energy calculations show that if you reduce the ply thickness, you can increase the strain to failure and the laminate strength, which is shown by the dispersed plies by the blue line. So the idea is if we further reduce the ply thickness using a spread toe fabric or UD tape, we can actually completely remove these damage modes and create a non-linear stress strain curve. So the material I've been using for this work is a carbon fiber epoxy prepeg of 0.03 millimeter ply thickness. The thing to note here is it's a very low volume fraction of 42%, which then leads on to the rather low Young's modulus shown by the mouse. And the other thing to note is all the strains have been captured using video excentrometry. So initial results characterizing the material showed that this is a plus or minus 45 laminate, and here we've got highly nonlinear response with strains in excess of 20% to failure. Also, the inset picture shows that there's large necking at the end tab region, which is a metal-like behavior, showing something similar to what you might get in a ductile material. The thing to note, though, is that the initial modulus is only 9 gigapascals, which is low. So the idea we wanted to try was, can we create a similar behavior but increase the initial modulus? So experimental testing and then analytical modeling shown that it is possible to do this with this material using a plus or minus theta 5 symmetrical configuration. So in the graph there's 25, 26, 27 and 30 from left to right shown, and then CT images on the right hand side of a plus or minus 30 and plus or minus 45, both showing that there's at failure absolutely no large scale damage in the specimens, which told us that this concept does actually provide the results that we wanted. So homing in on a particular configuration, I chose plus or minus 26 degrees, and you can see here Young's modulus is 35 gigapascals and the strength of 950 megapascals. And then the epsilon D at the bottom there of 1.4%, that's a pseudo-ductile strain, which is very promising. So moving on, we decided that we'd combine two aspects of Hyperduct's work. My work with the nonlinear angle-ply laminates, and then other work which has been done by Seal and Mesam on glass-carbon hybrid laminates, and using a thin ply carbon of the same material that I've used. The nonlinear stress strain curve that Gauguin managed to produce is shown on the right and the lower stress strain curve, and then the picture at the bottom shows the sort of tiger stripe pattern, as we're calling it, which indicates that the carbon layers are fragmenting and then delaminating locally to around the fractures of the carbon, but not propagating and not joining up, which is a key point which creates this tiger pattern. Now, this behavior can be adjusted or tailored depending on the ratio and the absolute thickness of the carbon and glass ratio. So it gives great control over the behavior and then the stress strain curve that we can produce. So coupling these two, we get a response very much like the one shown here, a metal-like stress strain curve with an initial largely linear loading up to about 2%, and then a plateau 700 megapascals up to in excess of 800 megapascal strength after further loading. This further loading takes place after fragmentation and delamination of the zeros, and then the angle-plies, which remain relatively undamaged, continue to take the load up to a failure which is similar to the value of the angle-plies by themselves. So obviously, how do we know what damage is in the specimen? It's key to know that and how it develops. So the CT scan on the right-hand side shows 5 specimens which are indicated by the red crosses on the stress strain graph. And these were loaded up to the points indicated, and we can see clearly that the pink, which is the dye penetrant, shows up the damage increasing as the strain increases. So we go from before fragmentation, absolutely no damage, and then gradually that increases through to close to final failure where there is extensive damage. And then zooming in on these specimens further, we were able to do a higher resolution scan on the two shown on the left. And this gives us a bit more evidence of fragmentation. So the yellow and blue insets on the central image show, hopefully you can see these lines indicated by the mouse, and their fragmentations and the center of the specimen in the 0 degree layers. To the right of that, we can show that the specimen which has been loaded up further has actually developed these large white areas of delamination where the dye penetrant has got in. And also another key aspect of this image shows that the damage is solely residing in the midplane of the laminate, which backs up the initial work of the angle-plies suppressing damage all the way up to failure. So further analysis and testing of these configurations using the analytical model, which is shown in the stress strain curves by the dashed line, shows us that we can have control over not only the fiber angle of the angle-plies, but also the number of zeros at the midplane. So that the plus minus 25 4 pairs with a 0 symmetric, that has 2 zeros obviously at the midplane, but the plus minus 26 with 3 pairs only has a single 0 at the midplane, which is denoted by the underline under the 0. And just by changing the fiber angle and the number of zeros, so the ratio and the absolute thickness, we can change the behavior. So the top is showing fragmentation and local delamination around those fractures, and then the bottom graph is behavior which shows no delamination and purely fragmentation. And obviously you can see here there's some inconsistency in the results, but overall the analytical modelling gives a very good prediction of the response that is actually seen experimentally. So to conclude, we've managed to show that thin ply, angle ply laminates have suppressed damage until final failure, which allows large fibre rotations to occur and a highly nonlinear stress strain behaviour. Coupling that with a fragmenting 0 at the midplane, we've been able to show an exciting metal-like pseudo-ductile response, which can be tailored via the adjustment of the ratio between the angle ply and the 0 layers and the absolute thickness of the zeros. Most importantly, this allows us to have a laminate which displays a gradual development of damage rather than a catastrophic failure at the onset of damage. So the key numbers here really are for the configuration in brackets. We have a failure strain in excess of 4.2%, which allows a pseudo-ductile strain of over 2% to be reached. Okay, thank you very much. My name is Jonathan Fuller, and you can contact me at the email address.